Well, and I remember the first time I started using the chalkboard, that in and of itself is a skill, like to be able to write legibly on the chalkboard, and now it doesn't even matter anymore. So, all right, so we're going to get into the planets today, and this is going to be a several. We're going to kind of take our time, since we have time to stretch our legs with planets, but everything we're going to talk about, I want to talk about in the context of how we extrapolate. What are the processes that are common amongst the planets? And we mentioned that before with the Earth. What are the processes that we see in all the different planets, so we can kind of do comparative planetology. So we're going to kind of go through this. We're going to mention a few planets, but then we're going to really focus in on the ones that NASA is spending a lot of time studying. And then we'll be able to just say, well, we can extrapolate this to how these processes work elsewhere. So try and keep in mind the processes. And I wanted to start with our solar system just because historically those are the planets. In fact, there is no definition for a planet outside of our solar system. There is a very specific definition for planets in our solar system that does not include Pluto. But there are no definitions for planets around other stars. Like, there's no official International Astronomical Union definition of planets around other stars. So I start, yeah.
That kind of makes sense. I mean, if we do meet aliens from other solar systems, we don't want to have to argue with them.
Right, exactly. Do we? Oh, yeah, they don't call that a planet. We do, yeah. But the reason I'm bringing this up is because these planets we're going to talk about represent an extraordinarily small sample of all known planets now. We have 8, 9 if you include Pluto, planets in our solar system. There are over 800 confirmed extrasolar planets in about 600 different systems or something like that. And there are 2,400 or so unconfirmed planetary candidates that we've seen transit in front of a star, right? So with all of those planets, our little 8 planets, we have to wonder, are we really seeing a representative sample of planets? For example, we're going to find out in a few weeks here that these planets called super-Earths, I think I mentioned those before, super-Earths, we don't have a super-Earth in our solar system, something that is between the mass of Earth and Neptune. But they are one of the most common types of planets we found around other stars. So they're about, if you figure Neptunes are one of the most common, super-Earths are as common as Neptunes. So if we have 2 Neptune-sized planets, we should have 2 super-Earths, and we don't. So are we an outlier in that sense? And we've never seen a super-Earth up close. So everything we're going to talk about when we start talking about these different planetary systems, you have to take with some perspective, because we're going to talk about processes for terrestrial planets, Mercury, Venus, Earth, and Mars, and gas giants, Jupiter, Saturn, Uranus, and Neptune, and we're going to make all these huge conclusions about the way planets work from that alone. And yet there's this class of planet that we've never seen up close, these super-Earths.
How common are hot Jupiters?
What's that? How common are they? Very well. We've found a lot of them because they're easy to find. But we don't think that, we think they're probably happening about 5 to 15% of systems, something like that. So we don't have hot Jupiters in our solar system either. And it could be that's why we don't have super-Earths, because most of these systems that have super-Earths also have a hot Jupiter. So maybe there's something about the process that forms super-Earths that leads you to hot Jupiters, or vice versa. In fact, that would make sense, because we're going to talk about how hot Jupiters are formed out far away from the star, and then they are migrated in. So if you're forming a hot Jupiter and you're forming a Uranus and Neptune, and then you migrate in before Uranus and Neptune get big enough to be Uranus and Neptune, you have a super-Earth. So it could just be our system didn't experience as much migration, and that's why we don't have any super-Earths. So. All right, so keep all that in mind, that what we're about to talk about, we're only talking about these planets because they are stuff we've studied up close, and so it gives us some context, but at the same time we haven't studied every type of planet up close. This is the planet Mercury, and just to give you a few fun facts about Mercury, the temperature between night and day is extreme, and the reason for that is because Mercury is in what's called a synchronous orbit. So, or I should say a resonant orbit, right? So it's not completely synchronous in the sense that the same face faces the sun all the time, but it's close. If I write down the orbital rotational period of Mercury, the rotational period is equal to 3/2 the orbital period. and the orbital period is about 88 days. So if the orbital period is about 88 days, that means that we get 2 rotations for every 3 orbital periods. And that makes the rotational period about 56 days or so. Does that work out? No, the other way around. Wait, did I do that right? 88p. Oh, right. 3 orbital periods equals 2 rotational periods. Yes.
So the day is shorter than the year.
Yes, that's right. So you get 3. You get 3 of these for every 2 of those to make that work out. Okay? Because if I have 2 times 3, it's equal to 3 times 2. Right? So 3 rotations for every 2 orbits. So the rotational period is about 56 days, roughly. And you multiply that by 2 and that by 3, you should get about the same number. So this is called a resonance because you have this integer ratio between the 2 periods. So if this is the sun here, that means that if I've got Mercury, not to scale, going around like this, if I have to go 3 orbital periods for every, or 3 rotations for every 2 orbital periods, that means if I go, how is that going to work? Got to go 3 for 2. So if I go around once, this is rotated 1.5 times. And I go around again, it rotates 1.5 times. Now, this wouldn't be at all interesting, except for the fact that Mercury has a very eccentric orbit. Its eccentricity of its orbit is about 0.21. So that's pretty eccentric, right? So what that means is that the closest approach, and this is again not to scale, but if this is the perihelion passage, perihelion, it's moving significantly faster in its orbit than it is at aphelion. So it's going faster here, which means the rotation is staying constant, but your orbital velocity is changing. So that means the apparent motion of the sun in the sky does some pretty crazy stuff. And so I wanted to calculate out for us what that does, because you get some pretty interesting dynamics there on the surface. And I just realized the total problem with this. I'm getting chalk all over my cool little iPad here. Oh, I could just put it up online. But then I wouldn't have anything to do. How do you prefer that? Do you prefer to be it on there or on there? Do you care? You really don't care? Oh, well. Here, I'll show you. I'll show you what I mean. Because I just realized I could just go over to our Canvas page. Forgive me while I stumble into the future. Have you found these pages where I've been posting all this stuff? Yeah? No? I saw several people say yes or no. Okay. There. Look at that. Do you prefer me to write that down? I think I should totally write it down. Yeah, I would prefer it on the board too. You can read that, but not from a distance. So, all right.
You wrote that on your tablet? Mm-hmm. That's pretty good.
I'm not bad. I'm pretty impressed. Yeah, I was surprised. I've been practicing though. I've been going to a lot of committee meetings and taking notes. So, all right. So let's take a look at what happens to the solar day. So remember the difference between the sidereal and solar periods, right? Sidereal is when the planet rotates with respect to the stars. Solar is when it rotates with respect to the sun. So what we would like to do is figure out what's the difference, effectively, between the angular speed of the orbit and the angular speed of the rotation. Because the rotation is going to stay the same. If I write down the angular rotation speed, or angular rotation rate, that's omega, omega rotation, we can calculate that as just 2 pi divided by the period of the rotation. But because we know that there's a relationship between the rotational period and the orbital period, I can write that as 2 pi over p orbital times 3/2, because we know we've got that relationship. And so that means that this right here is just the orbital angular frequency. So the rotational frequency is always 1.5 times the orbital angular frequency. But that orbital angular frequency is not constant, right? It changes. It changes with time. That would be the average, right? So this is the average orbital frequency, but the specific instantaneous orbital speed, orbital angular frequency, changes with time, because when you're at perihelion, you're going faster, and when you're at aphelion, you're going slower. And we have a very eccentric orbit. So what we can do is harken back to our, I think it's chapter 3, and we can use the equations for, this is for a circular orbit, we can use the equations for an eccentric orbit. And so I can write down that the angular frequency at aphelion is equal to 2 pi over the orbital period times 1 minus e to the 1/2 divided by 1 plus e to the 3/2. And I wouldn't expect you to just remember that, but you can go look it up in chapter 3. It's the angular frequency at aphelion. And the angular frequency at perihelion is 2 pi over p orbital 1 plus e to the 1/2 divided by 1 minus e to the 3/2. And those come out to, respectively, let's see here. This one is 0.67 times the average orbital frequency, and this is 1.55 times the average orbital frequency. So in other words, you're going 67% of the average orbital frequency at aphelion, and you're going 155% of the average at perihelion. So this is significant, right? But the sidereal period is the difference between the rotational, or sorry, the solar period is going to be the difference between these two. This is the apparent motion of the sun on the sky. So if I take this and subtract this, that's going to give me the apparent angular motion of the sun on the sky, how much it moves east to west. And so if I do that, if I take the difference between these two numbers, I get 0.83 of the average. So it works. It's going east to west at 83% at aphelion, what it would go east to west on average. But if I subtract these two numbers, what do I get? I get a negative 0.05. In other words, it goes backwards. So at perihelion, at noon, on perihelion, the sun stops in the sky and goes backwards at the rate of about, I think it's like 0.5 degree, 2 degrees per hour or something like that, significantly backwards. And then as you get further and further away from perihelion, it stops and goes forward again. So when you're at perihelion on Mercury, you see the sun stop in the sky, which I think would be pretty cool. Now, you'd have to be paying attention because noon, what's noon on Mercury, right? The planet rotates with a 56-hour sidereal period, or 56-day, so you'd have to pay attention. You could sleep through it. So you'd have to make sure you calculated it out and stayed awake for it. But it is something that's pretty exciting about Mercury.
So the sun does in the sky, in their sky, what Mars does in our sky, basically?
Yeah, it goes into retrograde motion, that's right. Yep. Mm-hmm. Yeah. It does it for a slightly different reason, right? But no, not really, because if you think of yourself as orbiting Mercury while you're on the surface. Now, this is sort of like, remember we talked about the epicycle definition of retrograde? This really is Mercury acting like an epicycle, but it's got to go faster. It's going at the epicycle, it's going the same speed, but then you're going faster at some point than another. So it's just an interesting little fact. Another couple of interesting facts about Mercury that are relative to our discussion of planets around other stars is that these resonant orbits where you have 3 to 2, 2 to 1, 5 to 2, 8 to 3, like there's all these resonant orbits. Those happen when the planet is very close to the central star. And there are stars where the habitable zone of the planet is within this tidal locking resonant zone. So if the sun was cooler and Mercury was closer, you could get a habitable world that has these 3 to 2 type resonances. And so imagine living on a world, you could imagine, it wouldn't be 88 days and 56 days, it might be 12 days and 4 days, but you could imagine a habitable planet where this exact same thing happens. And you would have to worry about that. In fact, I've been struggling really hard to figure out the exact orbital conditions of the Game of Thrones world. Right? You know, your Game of Thrones, they've got the long winter and then they've got, right? There's got to be an orbital configuration that gives you those properties. And I've tried to figure out what those are because I model all these different tilts and different orbital things. I haven't quite got it because it's not self-consistent, I don't think. But anyway, you could imagine a planet where, you know, one side is nighttime for a long period of the orbit. And so that would be like winter for all night. Anyway, you can think about that. The result on Mercury, though, is you get very hot days and very cold nights. Now, Mercury doesn't have an atmosphere. If there was an atmosphere on Mercury, that might modulate that a little bit. And one of the things that we don't understand, again, we don't have any planets with atmospheres in tidally locked orbits. So we're not exactly sure how that would work. If we take our climate models for the Earth and try to apply them to this situation where you could have an atmosphere on a tidally locked resonant planet, a lot of our assumptions break down, and it's very difficult to model. So if you're looking for a project that is, you know, get Mercury with an atmosphere modeled with a 3 to 2 orbit, and you've got something there. What could happen, right? Would you wind up with you know, habitable bands or so, I don't know. It's a very interesting problem. What's that?
On one side you got a nice atmosphere, like if you're on the side facing the sun, but if you're like perpendicular, then you jump on the tram and you run out of air.
Yeah, exactly. Yeah, no, seriously, because yeah, that's the question. Like some people would argue that for a perfectly tidally locked planet, so a 1-to-1 resonance, where the orbital period is the same as the rotation period, that the atmosphere would just freeze out on the cold side, right? But if there was any sort of circulation, that might modulate that. So you might have a place on the backside which is basically like the surface of the moon. And on the front side, you could have Venus. And then a band around the poles, which would be potentially habitable, but with really high winds. Right? Because, yeah. Anyway, nobody has successfully modeled that, just because we have no examples, right? I mean, you can't really do a very good job of modeling something if you don't have a good example. Speaking of something that is well modeled, Venus, stepping out from Mercury again, Mercury, just to put it in perspective, is what's the orbital distance for Mercury? I've forgotten. I think I've got it on my sheet here. The distance from Mercury to the Sun is, let me remind myself, I can't remember. I can go to the web here. If I can remember how to do this. Well, okay. Browser. Okay. It is average orbital speed, appealing perihelion, same major axis, 0.4 roughly, 0.38, 0.39. So it's about 40% of an astronomical unit away. If we go out to Venus, it is about 80% of an astronomical unit. So not too much different from the Earth, right? I mean, it's only 20% closer. But because Venus is just slightly closer to the Earth, or to the Sun than the Earth is, it has a hellish greenhouse effect. Now, I can tell you a story of how this happened, at least how we suspect it happened. We have no information of early Venus because it doesn't have a plate tectonics. So every 700 million years or so, the surface just kind of, because you got to get rid of all that radioactive heat, it just kind of rolls over. in this.
Like just break into pieces.
It just, yeah,
Like ice
yeah, kind of like that. Or there's massive volcanism, or the whole surface just kind of, we're not sure exactly how it happens, but if you look at the surface, it looks like you just took the surface and turned it upside down. So that's happening on Venus every 700 million years. So we don't know exactly what Venus was like, but the story goes like this. Early on, we've got a planet called Venus, which is the same size as Earth, and we assume the same composition, or very similar composition. So it has same surface gravity. It has some slightly different properties. It rotates slowly on its axis, and it rotates in the opposite sense. It's flipped on its side. So how that happened, I don't know. Nobody knows how that happened, but it's flipped on its side, and or it's flipped upside down. So it rotates in the opposite direction. It rotates clockwise. Yeah, because the North Pole points down is the way I think about it. So it rotates clockwise. The other way to say that is it's rotated in the opposite direction, but I have a very hard time imagining taking a planet and stopping it and spinning it in the other direction. It's much easier for me to imagine turning it upside down, like hitting it with something or torquing it around like that. So, so otherwise, the planets are the same. You've got Venus, you've got Earth. Earth has this little moon, but otherwise, the planets are the same. Venus is slightly closer to the sun. It's not that much closer. I mean, if you imagine a giant fire and you walk 20% of the distance to the fire, do you burst into flames? No. So it's slightly closer. So it's warmer. So imagine like the difference between, you know, Cincinnati and Brazil on average. So Cincinnati has about the average temperature of the Earth. Venus would have the average temperature of Rio de Janeiro. But that makes the water temperature slightly warmer, which makes the evaporation rate slightly warmer, or slightly higher, which gets more water vapor into the atmosphere. Da-da-da-da-da, what we talked about before, runaway greenhouse on Venus. And so we have a planet here which, now, why do we get all this carbon dioxide in the atmosphere to cause this greenhouse, is that as soon as the water's gone, the plate tectonics halts. You still have volcanism belching out all this CO2, but you've got no way to subduct it back into the mantle. And so the CO2 just builds up in the atmosphere, and in addition to all that water vapor and CO2, you just keep increasing the temperature until the temperature is about 470 degrees centigrade, night and day, because it's slow rotating with a thick atmosphere. There is no place on the surface of Venus that is not hellish. To put this in perspective, the surface temperature on Venus, the surface pressure on Venus is about 100 times what you're experiencing right now. And that's like going 1,000 meters beneath the ocean, which you can't do without a very specialized craft. So it's a pretty amazing place. Now, studying Venus, in my mind, from my perspective, this is the most interesting planet in the solar system because it's very similar to the Earth in composition and size. It's very close to the Earth's distance from the sun, and yet it's completely different. So if you were to do an n-member study of two different worlds, you'd want to study Venus and you'd want to study Mars. It has the most controls, or study Venus and Earth. You have the most controls on the experiment because you start with two planets that are the same and you get different results. The problem is going to Venus is really challenging because, yeah, well, for obvious reasons. Now, I do have a friend of mine, David Grinspoon, who has this idea of floating in the atmosphere. Did we talk about this?
Kind of.
Yeah, so you float in a giant balloon at comfortable temperatures, comfortable pressures, and then you just send stuff down. So it's more like oceanography. Maybe we'll do that someday. He's got a lot of crazy ideas, though, David Grinspoon does. Yeah, yeah. The Earth, I just want to mention, we've talked about the Earth already, but we talk about the Earth as being unique, and then we talk about planets being Earth-like, and I think that's kind of a it seems kind of strange. Like, wait, Earth's unique, but yet we have Earth-like planets. But the way I think about it is that there are properties of the Earth that are unique that other planets have a property similar to that, but not exactly the same. So for example, Venus is Earth-like because it's the same size as the Earth. But clearly it's different. Mars is Earth-like because you have volatiles at the surface that you find on Earth. There's water ice, CO2, water vapor, methane. So it's similar to the Earth that way. The moon is Earth-like because it's the same distance from the sun. But clearly it's not very Earth-like at all because it doesn't have an atmosphere. But then you get into other things like a moon we're going to talk about after spring break, Io, is a moon of Jupiter, is Earth-like because it's the most geologically active object in the solar system. The only other object as geologically active as Io is the Earth. So if geological activity is a special characteristic of planets, Io is Earth-like. Titan, moon of Saturn, is Earth-like because it has a nitrogen atmosphere that's very dense. It's also Earth-like because it has a fluidological cycle, except instead of water, it's methane. So you've got methane rain, you've got methane ice, and you've got methane liquid all at the surface. So if triple points are important, which the Earth has a triple point for water, then maybe Titan is an important world. And then the last one I'd mention is Europa, which has the largest liquid water ocean in the solar system, and it's a moon of Jupiter. So what do you mean by Earth-like? And I just want you to keep that in mind when we talk about these planets. Yeah?
What about Ganymede? Because I know like 30, 35 years ago, everybody thought Ganymede was the place to go to settle for a colony.
So Ganymede, Ganymede has, I think before we really looked at it, the way that people thought about Ganymede is that it was large enough to have, I mean, I'm trying to think of, there was some modeling early on that Ganymede might have had the liquid water underneath the surface. But Europa, when we go to observe it, appears to have the largest ocean. Now, there was this thing back in the day when 2001, 2010, where if you were to turn Jupiter into a red dwarf star by adding mass to it, Ganymede would be in the habitable zone. And that was the premise of 2010. I don't know if you've ever read that book or saw that movie where the aliens show up and start dumping monoliths into Jupiter to raise its mass, and then they made habitable planets. Because if you think about it, a habitable world around a red dwarf has an orbital period of 8 days, right? Ganymede has an orbital period of about 8 days. So it would be in the habitable zone. So that's probably where that concept comes from. That if you could make Jupiter a red dwarf star, which would be very hard to do because you'd have to increase its mass by about a factor of 10, right? Which would be hard to do. So again, when we talk about all these planets, these worlds, this is our metric, but yet there are properties of Earth that show up everywhere. Now, Earth is unique in the sense that it is the only planet that we know of that has both a triple point of volatile water, geological activity, right, and an atmosphere that can sustain a greenhouse effect. So it could be that the reason Earth is unique is because it has all of these Earth-like properties in one place. And it may be one of these things where you need all of this stuff in order for it to matter. Now Mars is the place we're going to talk about just because NASA is fascinated with Mars. Anybody have any idea why NASA would be fascinated with Mars? Why does anybody care about Mars?
Because it's cheap.
It's cheap. Relatively. I mean, compared to, well, the moon is, I shouldn't say, going to the moon is about as hard as going to Mars. If you look at it energetically, like if you calculate how much velocity you need to send a spacecraft to go up to the moon and land on the moon, it's the same velocity as you need to get to Mars. The advantage to going to Mars is there's an atmosphere, so you don't need extra fuel to slow yourself down when you get there. So that's why it's about the same amount of fuel. So it costs the same amount of money to send a robot to the moon as it does to send a robot to Mars. People, the same thing. It costs just as much money. Well, I take that back. If you're billing per diem, it's a lot more expensive to go to Mars. But did you hear? I was on the radio last night. Douglas Tito. He was the first paying customer on the Mir satellite or Mir space station. Is talking about sending a couple, a man and a woman, who are in a long-term relationship for a long time. He's going to select a couple that has shown this attribute on a 501-day flyby of Mars, free return trajectory in 2018. You buy that?
Really hope they don't get in any fights along the way.
Now, Stacy and I are perfect for it because we once spent 30 days in a Nissan Sentra going to the Grand Canyon. So I'm like, let's sign up. It'd be perfect, right? Because we got the, if you can spend 30 days in a Nissan Sentra with somebody, that's why we got married. Because it was our first date. Seriously. We're like, hey, she said, you want to go to the Grand Canyon? I said, sure. We hopped in the car. 30 days later, we got back, and we're like, we should probably get married, because that was, if we can handle that, we can handle anything, right? And they're going to send these people for 501 days. Now, it's free return trajectory, so it doesn't It doesn't really cost anything. They're not going to land on Mars. That's the part we don't know how to do. How do people land and live on Mars? But we know how to have people in space stations. We've had, I mean, the Mir astronauts, there have been people who've been up in that place for what, 280 days, 320 days? These Mir astronauts, those Russians were serious. Remember, because their whole country collapsed while they were up there? And it took a while to get a rocket back, so they were up there for 11 months, and then they were up there for 16 months. And so they're saying, well, you know, we've done it before, we'll just go to Mars and back. It's just a big space station trip. Anyway, pay attention to that, and let me know what happens. I'm going to be paying attention, because they're saying 2018 they'll launch. They'll be back in 2020. Now, at the same time, there's a group called Mars One. Do you guys know about all this stuff? There's a group called Mars One that's talking about sending people to live on the surface. No come back. We send craft, you no come back. Like, seriously, they're going to go all the way to Mars in 2020. They send the first craft, which has a robot that will land and set up the habitat. And then they come in. Yeah, and they come in the next one, 4 people in 2022, 4 people in 2024, 4 people in 2026, and then they'll just daisy chain them together. And they're talking about having a colony, again, permanent. They're not coming home, and people are signing up for this. Now, they're funding this through a reality TV show. Now, whether they actually get to Mars, it's probably still going to be a pretty interesting show. They'll probably make a ton of money. And I have friends on both sides. Some of us are really excited to see them try. Other people think they're just charlatans, right? They're just promising something they can't deliver to get advertising for the reality TV show. We'll see what happens. But Mars is interesting, and NASA likes Mars because it's relatively cheap to get to, and people can walk on the surface. This is important, right? People can walk on the surface, and in principle, people could live on Mars. The moon, you would have to import everything, right? Even the air. Well, and you have to import the air, well, you have to manufacture the air on Mars, but at least you have the raw materials. You've got carbon dioxide right there. So if you have some sort of, you know, opposite catalytic converter that you have in your car, just run it backwards and you can turn CO2 into oxygen and CO, right? Because that's what your catalytic converter does. Your catalytic converter turns CO into oxygen, or CO and oxygen into CO2. So you just run your catalytic converter backwards. So in principle, there are some raw materials on there, and the soils have organic materials, and so it wouldn't be as easy as, you know, coming to Boston and setting up a colony, but it's in principle you could imagine doing it. This was somebody who imagined that it had already been done. Anybody ever heard of Percival Lowell or been to the Lowell Observatory? Percival Lowell was one of the early astronomers in the late 1800s and early 1900s who built one of the best telescopes ever in the deserts of Flagstaff, Arizona. And the Flagstaff at the time had no people living there. It was very high, very dry. He had one of the largest, best telescopes with the best optics. And he was particularly fascinated with Mars. And keep in mind, the only way you could do observing at this time is to look through the telescope and draw pictures. There's no photography, right? You look through the telescope, you draw a picture. And this was good in the sense that the human eye, especially for planetary science, looking at the planets, you can see amazing detail for short periods of time that would get washed out on a photographic plate. And try this sometime. If you're ever looking through a telescope at, say, Jupiter or something like that, you watch it, it'll be this fuzzy blob because of the atmosphere, but then this particularly still patch of air will go over. And suddenly, for a fraction of a second, it's just crystal clear. Best resolution you can get from any telescope with your eye. You know, arc-second resolution, because you did the calculation with your eyeball. You can get really good resolution with your eye, provided the atmosphere isn't moving around. So you get these really beautiful, clear windows of wonderful clarity for a fraction of a second. So he would memorize that and draw it. He'd sit there all night doing that. And he came up with these pictures that look like this. He saw detail that nobody else saw, which is a little red flag in science, right? his argument for why nobody saw this level of detail is because nobody had a telescope as good as his in a site as good as his. And he not only came up with these pictures, but he came up with stories for what he was seeing. So you'll notice that these are the polar regions, right? And you'll see these very sharp linear features that go from the polar regions to the equators, and then you see junctions, right, of all these linear features. And so what he saw, what he started to write about, is cities on Mars. And he had this whole mythology in a way. His explanation was this was a dying civilization on a desert planet that was hauling the last of its resources that it could from the polar regions, which were inhospitable, to the equatorial regions where they all lived. And this permeated the culture so much that he wrote a book, and it was in our library. I don't know if it's still there now, but he wrote a book, Life on Mars. And it's very well detailed. From his observations, the sociology of the Martian culture, all sorts of crazy stuff in there. But the funny thing is based on his observations, there was no reason to, if his observations were correct, his conclusions were valid. Maybe a little bit speculative, right? But there was no reason not to think that there might be people up there. So imagine from 1870 to 1920, 1930, 1940, a vast swath of the popular society and scientific community believed there was life on Mars. So think about what that would be like, where we would just take it for granted that there are people on Mars. Like, well, yeah, there's people on Mars. Look at Percival Lowell's stuff. Now, there were a lot of people in the scientific community who tried to validate this. They didn't see any of this. This is a modern representation of his canale, or his canals, and what it actually looks like through the Hubble Space Telescope. So clearly, he invented some things. Maybe he had, I don't know, stigmatism on his eye he didn't know about or something. Some of the things he got right, like these bulk features here you can see, but there are no linear features to speak of. Now, the interesting thing about this is that despite the fact that we started to get better and better observations, and the scientists started to kind of retreat from the idea of cities and civilizations, the general public was hooked. They bought it. Everybody thought there was life on Mars. Scientists, I mean, up until we sent the first probe, some people even still thought this was vegetation, this sort of bluish, greenish stuff. So, and again, they had reasons, and there were scientific papers written about it, but the general public, they were convinced there were aliens. And in fact, the science fiction of the day, War of the Worlds, right? H.G. Wells, it was done, now H.G. Wells' War of the Worlds was written 1905, something, 1910, something like that, right? This is 1938. They did a radio play with Orson Welles, and everybody bought it. And because they did it like a reality show, he's like commenting on the game or the news or whatever, and then suddenly, oh, this just in, there's been a craft that's seen out in Grover's Mill, and they started reporting on it, and they just went straight into the radio play, just like the book, because that's how the book starts. And people panicked, because they actually believed aliens were coming. And that's how much culture. Now, even after this, they had to come on and say, no, we're sorry, this is just a radio play. But that didn't matter. People still thought there were aliens on Mars. It wasn't until we started taking pictures like this where it became obvious that Mars was not a place where you could have alien species. In fact, not even a place where you can have trees or lichen or anything. And the problem what happened with that is we had this mythology of the Martians, and then we took pictures like this, and then that ended. People said, oh, the Mars is just like the moon. The Mars is the moon. Not interesting. For decades, right? We landed Viking in 1970-something and didn't go back until 1996 with a rover. Because the people who pay the bill were like, what, no aliens? Pfft, I don't care, right? So you'll notice now when we talk about Mars, their focus is on finding habitats for life, and they push that, push that, push that. And luckily for NASA, they're finding potential habitats for life. Otherwise, I mean, if we went up there and it was just Mercury, I bet you we wouldn't be there. Because it's the thing people care about, and the thing people want to spend billions of dollars doing is studying life. Now, I didn't get interested in Mars because of life. I got interested in Mars because of the atmosphere, because it's so different from the Earth. And yet, you see similar geological processes on the surface. And so how can you have a place that has an atmosphere that's so tenuous? To give you an idea of how tenuous the atmosphere is, on the surface of Mars is about like flying at 100,000 feet on the Earth. If you were to step outside of a U-2 or something like that, right, not breathable. Everest looks like paradise compared to the pressure on the surface of Mars. The other thing is, but the other thing is that the temperatures are not that bad. Right? Like Antarctica winter-summer temperature variation, that's like Mars day-night temperature variation. So you go from minus 80 Fahrenheit to plus 30 during a day. So you could imagine, I mean, it'd be kind of crazy to think about what that would feel like. Of course, the atmosphere is so tenuous that it's much colder at your head than it is at your feet. Because the ground, you've ever been outside on a sunny day in winter in Utah and the ground's really hot, but yet your head's still cold? Well, it's even worse on Mars, right? The temperature gradient's enormous. We do have ice on Mars. This is the northern polar cap. This is water ice. So there are resources on Mars that you could use if you happen to live there. There's also ice in other forms in the regolith, which is what we call the soil. So it's like Earth, it has these polar caps. It also has snow. This is the Viking rover, Viking lander. It did not rove, it landed. But it took this picture, it was up there for 2.5 Mars years, and it would often wake up in the wintertime to snow. Right? Now, I mean, it's snow. It was more like frost, but it was water ice that condensed out of the atmosphere. And it was gone as soon as the sun came up. But so you have a place that is not so dissimilar to Earth. You've probably been to places in southern Utah that looked a little bit like that. One thing that Mars has that Earth doesn't have is this giant volcano. This is Olympus Mons. This is the size of the state of Arizona. Okay? It's so tall that it sticks up out of the atmosphere. Such as it is, yeah. It's about 24 kilometers tall. Everest is 8. Now, it's so big, though, that if you were to climb it, you probably wouldn't even know you were on a slope. The slope is so, I mean, so you do what Arizona is 300 miles across, or let's say 600 kilometers across, let's say. So 300 kilometers is your run, and your rise is 24. So it's like a, what? Is that a 10% grade?
Yeah, a little less than
10% angle, not 10% grade.
Yeah.
Yeah, because isn't 6% grade? That's pretty steep. Anyway, so it's not, it's it's not, it's a 10 degree angle, not 10%. That's what 10 degree angle. Wait, is that right? No.
It's a little bit less than 10.
No, it is 10%. Yeah. Well, I'm doing my calculations strange anyway. Well, it's not very. It's big, not very tall compared to how big it is.
It wouldn't be so much a climb as it would be a random hike across half of Arizona.
Yeah, with a slight grade. Yeah. Now this is the other feature on Mars that you don't get on Earth are these massive dust storms, right? This is about the size of the United States right here. Okay, so you get dust storms that, now, well, that's nothing compared to what they can get. Dust storms on the Earth happen, but then they go into the ocean and the ocean sucks up all the dust, right? So eventually you don't wind up with very big dust storms. These are similar sized dust storms on Mars and Earth, and you see similar dynamics, but there's no ocean to soak up the dust. So what happens if this just blows and blows and blows and blows and picks up more and more dust? You get something like this. Now I saw this with my own eyes. I went outside in June of 2001 and I noticed the normal little red Mars that you always see up in the sky. And then a few months later I went out and it looked like yellow. I'm like, I've never seen Mars look that color before. And then lo and behold, the Space Telescope images came out and there was a planet-wide dust storm that you could see from Earth. Right? And because I mentioned to my professor, I said, Mars is yellow. He's like, maybe it's a planet-wide dust storm. And then we looked up these images. Right? So you can see that these dust storms go planet-wide. And this is my main concern about sending people to Mars. Because if you want to know what this dust storm would be like, anybody have a young child that you can borrow? Anybody have any children? Nephew, little brother, perfect. Nephews and niece, grab one. Give them a box of cake flour in the kitchen, and then turn on one of those big industrial fans and have them do this, and then try to clean your kitchen. you'll never get that stuff up. I mean, this dust is so fine that it would blow through, it would be in your spacesuit, it would get inside your spacesuit, it would get inside your habitat. I don't know how they're going to deal with this. Keep the habitats at positive pressure, I don't know. But it's going to be a real challenge to figure out how to get people to deal with this. The other thing about Mars that's so different from the Earth, because of all these winds, you get dust devils. These are dust devils, 40 kilometers. This is in projection, that's 20 kilometers. So this is effectively a, 15 kilometer tall, or no, it's got to be bigger than that. 30 kilometer tall dust devil, 30 kilometers. That's pretty remarkable. There are smaller dust devils. This was a picture from the Opportunity rover, just watching these dust devils go across. So wind dominates the surface of Mars today in a way that it doesn't really impact globally the Earth. Globally, Mars is impacted by wind quite a bit. Just to put this into perspective, these are Earth dust devils, which is like the one you just saw, a little tiny one. This is a tornado. That's a Mars dust devil. So imagine standing there on the surface of Mars and seeing this dust devil go by that is 30 kilometers high. Well, sorry, this one's only 8 kilometers. It doesn't matter, 8 kilometers high. But you could just stand in the middle of it because the atmosphere is so low density. It wouldn't. You could stand in a 200-mile-an-hour wind on Mars and not even notice. It would be like, because it's so low density. So Mars is a different place, and there's Olympus Mons for perspective there. Okay, so let's look at the topography of Mars. This picture was taken using a laser raster scan of the surface. So we know more about the surface of Mars than we know about the surface of Earth, because the Earth is covered in water. And so in order to get this type of detailed topography, you have to sit on the surface of the ocean and send radar down and just mow the lawn on the ocean. Back and forth. It takes a really long time. This, you just send an orbiter around with a laser beam, do the time pulses back and forth, you get great topography. And you see some pretty interesting stuff. This is called Valles Marineris, United States. It's a really huge canyon. This is Olympus Mons here. We've got the Tharsis volcanoes. And you start to look at some of the processes here, and I mean, can you think of anything, or you point anything out on here which captivates you, other than the volcanoes and that giant crevasse? You see anything of interest?
Looks like a continent.
It does. This does look like looks like Australia, a little bit upside down. But look at this right here, and this right here. That's what it looks like, except it's the size of the United States of America, right? So what this is, likely, what we're seeing, is that when this cracked, for whatever reason, crust cooling and weak spot, whatever, when this cracked, it released a ton of liquid, most likely water, that blasted across the surface, equivalent to the United States of America. Now, we see stuff like this in the US. At the end of the last ice age, there were huge ice dams covering Idaho and Washington. And when those let loose, they created what's called the Washington Scablands, made a huge catastrophic flood. But it's the size of the corner of Washington. This is the size of the United States. Right? So this must have been an incredible sight to see when this happened. So I showed this to you because you can see that there's volcanism, there's fluid flowing, most likely water, and clearly Mars has had a very complex history. I showed this to a geology student once, and they noticed something interesting, that this is all lava flow, right? You can see how that kind of flowed out. And they asked why the volcanoes were all in a line, and why is through the cluster right there. I've got another picture of this here. Hopefully. No, I don't. But the main idea is that on the other side of the planet, there's a giant impact crater that's about a third of the size of the planet. And so if you imagine taking a planet and smacking it on this side, the pressure waves travel through and basically create a weak spot on the other side, and that's where all the volcanoes blast through. That's a geological interpretation of why all this shows up in the same spot. Now, this is catastrophic flooding. It probably happened all at once, probably happened a long time ago, and it probably happened because of volcanism or something else. What's more intriguing on the surface of Mars are things like this. This is a relatively high-resolution image. Weber State Campus would be about like here. Okay, so just put in perspective, it's like looking across a relatively, like the Little Grand Canyon down in Price or something, or down in Carbon County. Near Emory. It's just a canyon. But what do you notice about it? Other than the fact that it seems to be a little meandering canyon, which is indicative of something flowing. But what else do you notice? What's that? Yeah? Okay, yeah, so you've got, something coming in like this. What about as I come down this channel? What's this? You see that? It looks like a channel within a channel, right? The last place I saw a channel within a channel was the Grand Canyon, where you've got this huge canyon and then there's the Colorado River. So how does the Grand Canyon form? The Grand Canyon forms because you've got uplift on the Colorado Plateau. You had a river, the land is uplifting, the river is eroding, and after a few million years, 16 million years, you get this huge canyon. This is indicative of continuous flowing water, which is a different animal than episodic flowing water. Episodic flowing water is easy. You blow up a volcano, liberate a bunch of ice from the subsurface, it flows on the surface, evaporates, never happens again. This means there had to have been some kind of continuous flow. And it gets even better, right? If we look at some of these craters, this is a big crater, right? This is the northeast of Holden Crater. We're going to go zoom in on some of these areas here because we have high resolution imagery, and you start to see, this is 1,000 meters, Weber State Campus. What does this look like? It looks like a river delta. In fact, if you think this is Weber State, if I can overlay on this Weber State, mouth of Weber Canyon, river delta, Hill Air Force Base, the topography is the same, right? Because you had a river flowing into a lake. This looks like a river flowing into a lake. There are also places where you see oxbows. I don't know if you can see those. Crisscrosses, which tells you that not only was water flowing, but it flowed enough that it had different paths, took different tracks through this area. And so again, this is pretty compelling evidence for something that's either happening repeatedly over short time scales or continuously, or geologically continuously. Now there's even more recent evidence, and this is something I was just reading. They have a new instrument out called HiRISE, which can see even finer detail. These are recent because there are all these sand dunes down here, and this is debris from a ridge that's covering them. And the sand dunes form all the time, which means these have to be happening today. So we're not just looking at some old geological history of Mars, we're seeing stuff that could be happening as we speak. And if that's the case, that means there's liquid water habitat someplace on Mars. And I think that's pretty captivating, because liquid water on Earth, every place we ever go, find liquid water, we find life. Mars and Earth have been trading material back and forth like, elementary school kids trade gum. Do they still do that? Nobody did that when you were young? I didn't do it, but my friends did. It was nasty, right? But we blast meteorites off of Mars, they land on Earth. We blast meteorites off the Earth, they land on Mars. They're swapping material, right? So if you've got microorganisms on that rock, and it lands on Mars and gets into a habitat, why wouldn't they thrive, right? So this is pretty fascinating, and it's the whole motivation for why we're sending rovers to Mars, to be able to rove around and look at this. Now this is the Opportunity lander, and I'm gonna focus on Curiosity, but I wanted to show you this because this was the first outcrop we had visited on Mars, up close. So the Viking lander didn't see an outcrop, it just saw a rocky plain. And the reason outcrops are interesting is because they're in place. And it's showing layers of material in place. So we can do some real geology and try and get a story. This was one of the first pictures from the Opportunity rover, and I love this one because when this picture came out, it was one of the first pictures, and they called it the Great Wall. This was before they got the 3D camera going, and it's like this tall. It's a lot closer than they thought. So this is just an up-close view. So you can see layers of material. And again, this looks pretty like southern Utah. Like you've been places that look like this. This is where we've landed on Mars so far. This is Viking 1 and 2. That was back in the 70s. Those were static probes that just sat on the surface taking weather and atmospheric samples. They also had a little arm to scoop up material. A little bit later, if you want, we can talk about the Mars Life Experiment, which was inconclusive, right? Pathfinder was a 20-year gap between Viking and Pathfinder. And Pathfinder was one of these ones where they had this crazy idea that they would land it in a bouncing beach ball. And the NASA people said, this is nuts, it'll never work, but here's a little bit of money, just try it. And then it became the way to get to Mars, which we then sent Opportunity and Spirit to land using the beach ball method. Phoenix landed by regular retro rocket onto the surface. And then that brings us to Curiosity, which kind of was a hybrid model, if anything. And I've got a little video to show you about that. But before I show you the video, let's look at where we went on Curiosity. So again, the focus is on present and past liquid habitats. They chose Gale Crater because it had a relatively smooth basement to land in, but was close enough to a large outcropping of rock that they could go visit. And in particular, it looks like there's a little, I don't know if you can see this from where you are, it looks like there's a little channel coming down here, one here, there's this one over here. So it seems like there are multiple areas where something flowed into the bottom of this crater. Land in here, and the idea is over the next 2 years to traverse up to as close to that mountain as we can get. That's the plan. This is from that elevation picture I was showing you. This is the canyon they're trying to get to, and this has highlighted what would be the alluvial fan. You can't really see it, that's why they highlighted it, but any material from here should be here. So if it can drive anywhere close to this, it should be able to get at some of the material and see what's going on. So let's watch a little clip here. You've probably seen this, but I'm going to have you watch it again. Have you seen this? Who's seen this? Okay.
It looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought. But it still looks crazy.
That's not very much code here.
The top of the atmosphere, down to the surface, it takes us 7 minutes.
Now this is all CGI, but it's based on real data. So.
For the signal from the spacecraft to make it to Earth, that's how far Mars is away. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
Slammed into the atmosphere, it develops so much aerodynamic drag, our heat shield. It heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we have never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time for the rest of the landing sequence to work.
This big, huge parachute that we got, it will only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we gotta cut it off. And then come down in rockets. Once we turn those rocket motors on, we don't do something. We're just gonna smack right back into the parachute. So the first thing we do is make this real radical diversion. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with this radar and see where we're going to land. And we head straight down to the bottom of the crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent state, it's a collision force with the rover. You must cut the throttle immediately and fly to the descent stage to a safe distance from the rover.
When I saw that for the first time, about 3 months before landing, I thought, that's never going to work. That is never, ever, ever going to work. But it did. It did work. And the crazy thing I was mentioning before some folks came in, they didn't test it end to end before Mars because there was no way to do it, right? You can't launch it on Earth's atmosphere. How does that test anything? So they tested all the components and they put it all together, and so it's a testament to our way of modeling things and the engineering teams. It's just amazing. Now this I wanted to show you because this is the actual descent video. So they had a camera on the rover and they took pictures as it came down. So what you're seeing here is the real descent imagery. So there goes the lens cap, that's the heat shield. And you can see this dune field, right? And you can see some scarps and some of those rocks, and you can see the craters, and you can see an ad for Google Chrome, which is important because this is how we pay for space travel now, is by product placement. You can see some very interesting kind of scarp sort of things around here, and then you saw where it stopped and started using the sky crane, and then it comes down here and you'll see a little bit of dust up from the rockets, and then oh wait, sorry, that's where the sky crane starts going down. It did create quite a bit of dust, but not enough to wreck the instruments. And then we can see where the heat shield hit. Yeah. So it's crazy because we've got all these instruments around Mars to look at these things from space.
I think it's so funny, you know, having done enough programming in my life, I think that they were talking about how important it was that the computer does all of this, all on its own and everything. Only 500,000 lines of code. That's next to nothing. I mean, that's
well, and that's because there's not a lot of room on the you know, these are not powerful computers. These computers were flight tested 30 years ago. So, all right, so you can see some pictures. Again, how do we get these pictures? We have high-rise camera that's going around Mars. But it's pretty cool to kind of just do like a little post-mortem here. We've got the parachute and the back shell. We've got the sky crane where it hit. There's the heat shield over there, and you can see where we did, you know, blast up a little bit of dust, and that's where Curiosity landed. And so we're very close to some very interesting features. This is again looking down on where we landed, And one of the first places they were driving to is this over here. Now, what do the instruments on this thing look like? The instruments have a very high-resolution binocular camera, which they're using all the time while they slowly march across the surface. Now remember, because this is Mars and the light travel time is 20 minutes at best, you can't drive this like a robotic car. You have to send instructions, it has to do something, and then it has to send you back a report, and then you send instructions and it does something. So it's kind of like that, did anybody ever play that game Logo with the turtle, right? There's a basic, you get a little program and it has to go someplace, and then you get a report of what happened. This was one of the first pictures coming down. You can see what the surface looks like. This is some of the pictures they took right after they took off the mass camera lens and lens cover and started looking at features here. Looks very similar to southern Utah. You can see in the distance dunes and ancient dunes that have been sort of solidified. This is a, let's see if we can get this to go. This is a panoramic shot panning across that whole site. Again, I've camped here in southern Utah, right? You can see off into the distance some of the rocks and outcrops. Now the exciting thing about, well, we should probably do that again, huh? Just one more time. Yeah. So the rover can't get to everything, but with this high-resolution binocular camera, it can look at a lot of very interesting features and decide where it wants to go, or decide where we want to send it. So some up-close pictures of, if you look off into the distance, oh yeah, can you see this, this channel? That is so captivating, and it looks like a road. It's not a road, it's a channel coming down. So that's where we're going in 2 years. It's going to probably take that long to get there. But here's the thing though, where they started looking around, this was just a few weeks after it got there, and they saw these cemented layers, which is pretty interesting. But if you look closer to some of these layers, you see, and this blew my mind, you see gravel. Now how do you form gravel? Water, right? Why do we have so many gravel pits around Utah? Because this used to be a lake with all these rivers flowing into it. And that's why we have Stake of Starker Parsons and all these gravel pits around here. So this is gravel. You can only form this with relatively long duration flowing water. And honestly, I came from the camp of you can't have liquid water flowing on the surface of Mars ever. The physics just doesn't work. And they would show all these geological, this looks like a channel, this looks like this. I'm like, I don't care. You can't do it. This convinced me. As soon as I saw this, I just threw up my hands and said, yep, you're right. There's water flowing on the surface at some point. Because it's, I mean, look, compare it to Earth. This is a gravel bed in your backyard, right? You can find this in Ogden Canyon. And we know that the Ogden Canyon gravel beds were part of an ancient river, or a river that flows into this. So to put that into perspective though, I think that that means Mars, maybe planet-wide, could be a lot like the Great Salt Lake, right? The Great Salt Lake is episodic. We don't have continuous flowing water from tons of rivers, right? We have a drying up lake bed. Well, maybe on Mars, it doesn't dry up in 10,000 years, it dries up in 2. But then shows up every 5. Imagine that, where you get this huge lake every 10 years, and it lasts for a year, and then it dries up. That could happen. So where are we going with this? And I just want to end with this before we take off into spring break and come back next week. These dates are a little bit off because we had that whole recession thing, which pushed everything out about 2 years. But we've landed Phoenix. Mars Science Lab, which is Curiosity, is on the ground. And depending on what it finds, we're going to go to one of these tracks. And so far, it appears that not only is it finding evidence of past habitats of liquid water, but it's finding some possible evidence where something has happened relatively recently. And so I think the next mission is going to focus on searching for hydrothermal habitats which might have present life today. And then where do we go from here? Well, NASA has plans, sequester willing. NASA has plans to complete what's called a scout mission for an atmospheric mission to study the atmosphere. That's already in place, but then they've got plans for a science orbiter, which will be a new support craft around the surface. And European Space Agency is talking about sending ExoMars. Again, these dates are a little bit, this should say 2015 because we're a few years out. By 2016, 2018, we're talking about having another, even more capable rover on the surface. And then by 2020, 2025, having sample return. Now, overlay on top of this, what's been happening in the news with commercial spaceflight over the last year is just astounding. I mean, really, in the last year, we have had how many companies pop up to do commercial spaceflight, either supplying the International Space Station, which had never been done before, by a commercial space flight. They're talking about putting people in orbit on the station, taking people back and forth from the station. There are at least 2 groups that are talking about sending people around or to Mars on this same time scale. We've got folks in Pasadena who are already planning to mine asteroids, and they're sending probes out in the next couple of years. So I throw this up there with, like, you know, NASA does space travel and this is the way it's going to go, but this is all up in the air, because I can tell you for a fact that if there are people on the surface of Mars in 2020 or 2022, which is what Mars 1 is talking about, all bets are off. Forget sample return. We'll just ship an MSCM and let them do the work up there. So it's a pretty crazy time, and there are a lot of people making some amazing claims about planetary exploration. I will leave it to you to decide whether or not they're actually going to do it. But the money's there. It doesn't cost that much. The technology's there. NASA drags its feet a little bit. So this could be out of NASA's hands. But anyway, that's NASA's plan. And again, it's Mars sample return. I sort of see this picture and I want to put like tourists with cameras, because NASA's going to land at sample return and there's going to be people up there, oh, cool, there's NASA. All right, so that's going to end our trip through the terrestrial planets. On next Tuesday, you won't be here. The following Tuesday, we're going to talk about the Jovian worlds. We're going to do the moons of Jupiter and Saturn. And then I think after that, we get to talk about extrasolar planets. We haven't talked about those yet, have we? Whew, that's going to be exciting. All right, you guys have a good spring break.